Dear students, Assalamu alaikum. In this tutorial, we're going to learn tabulation method. So here is the question for our problem. Simplify the function using tabulation method. So here is the given function. So we're going to solve this problem in two parts. So we're going to describe part 1 first. So here is part 1. At first, we're going to take our question and we're going to write the mean terms sequentially from using an ascending order. Alright. So here the mean terms are written in ascending order and their binary bits are also written alongside those numbers. Alright. So the binary bits are written using 4 bits. Alright. So why did we use 4 bits? That's because the highest number given here is actually 15, and 15 can be represented by using 4 binary bits. That's why these binaries are written using 4 bits. And you can also see that there are 4 variables mentioned here, w, x, y, z. So from this case, we can also know that we're going to write those binary numbers using 4 bits. Okay, so the first step is to write all these main terms sequentially in an ascending order and also write their binary digits. Okay, so now we're going to create our step 2. So from this step, now we're going to group those binary numbers based upon number of ones in them. So we can see that from these numbers we can actually create 4 different groups. Group A, B, C, and D. So group A is actually indicating those numbers which have only 1 in them. Alright. So for group B there are 2 ones in them, for group C there are 3 ones in them, and for group D there are 4 ones in them. So we're going to group the mean terms based upon number of ones in them, and then we're going to put them into a different table, and that will be our step 2. So in step 2 we actually just divided all of our binary numbers into separate groups based upon number of ones in them. So our groups look like this one right now. So there are 4 groups in step 2, group A, B, C, and D. So now what we're going to do is we're going to find single bit difference from step 2. So how can we actually do it? So we're going to compare. So we will compare all the mean terms of group A with all the mean terms of group B, and then we're going to compare all the mean terms of group B with all the mean terms of group C, and then we're going to compare C with D. So basically what we're going to do is that we're going to compare only one group to its immediate next group. Alright, to its immediate next group. That means we're going to compare A with B and B with C and C with D. That's it. So let's just check a simple example. So at first we're going to compare 1 with 6. Alright, then we're going to compare 1 with 9, and then we're going to compare 1 with 10. So that's just for the comparison of 1. So we're going to do the same thing for the later ones. Like we're going to compare 4 with 6 and 4 with 9 and 4 with 10, and then we're going to compare 8 and 6 and 8 and 9 and 8 and 10. So after that our first 2 groups will be done. So we'll be finished with the comparison of group A and B, and then we'll compare B and C and D. So the whole comparison part will actually look like this. So we're going to compare A with B and group B with C and group C with D. We're not going to compare A with C or A with D, alright, because C and D are definitely not the immediate next groups for A, and we're definitely not going to compare B with D because D is not the immediate next group of B. Alright, so we are only gonna compare one group with its immediate next group. Okay, so let's continue. So during the comparison we're going to compare all the mean terms of one group with all the mean terms of its immediate next group. So at first let's check the scenario for A and B. So we're going to compare 1 of group A with all the elements of group B. So at first we're going to compare 1 and 6, and here you can see that we have written them individually right there. Okay, so what are we trying to get out of here? So we're trying to find single bit differences. So let's see, for 1 and 6 you can see the binary numbers are written over here. So we can see that there is 1 difference and then there is another difference, and then there is another difference. So there are basically 3 bit differences over there. So we cannot consider it, we cannot take that, we cannot take this pair, so we're definitely going to discard it. So let's check the next comparison. So we're going to compare 1 with 9. So you can see that we have only 1 bit difference right over there, and all the other bits are actually the same for both 1 and 9. So there is only one bit difference, only single bit difference. So we're definitely going to consider this pair, 1 and 9. So we're gonna take it into consideration, and we're gonna put that into our step 3. All right, so this is what is actually written here. So this is the step 3. So since these pair actually match the condition of single bit difference, so we took this pair and put it into step 3. And in step 3, you can see that there is something written over here, some binary bits and a dash. So how did we actually put it? So here is the rule. We'll put a dash at the position where we find the bit difference, and place the pair in step 3 as we did, and the other bits remain same for both the digits of the pair. Alright, so here you can see we have found the difference at the very first position of this pair. Alright, so that's why at the first place right there is a dash, and all other bits are actually the same. That's why all other bits remain the same, 0, 0 and 1. Only at the first position we got the difference, that's why there is a dash. So that's how we're gonna be putting different pairs into step 3. So let's continue our comparison. So after that, we're going to compare 1 with 10, and you can see there are 2 bit differences, so we're definitely going to discard it. So now the comparison of 1 with all those numbers are done. So now we're going to move on to 4. So you can see when comparing 4 with 6, 9 and 10 from group B, we can see that only 4 and 6, this pair matches the condition of single bit difference. So there is only 1 bit difference right over there at the third place for 4 and 6, and since this is the there is only single bit difference, so we're definitely going to consider this pair. And for other pairs, we have found more than 1 bit difference, so we're going to discard it. All right, so for 4 and 6, we're going to put them into step 3, and we're going to write the binaries with the dashes. So how can we actually do it? So the difference was found at the third place from left side, the third place. So here you can see that at that specific position we have put a dash over there, and all other numbers actually remain the same. So this is what we get for the pair of 4 and 6. So we'll continue our checking for 8 now. 8 will be compared with 6, 9 and 10, and you can see that if we compare 8 with 6, 9 and 10, we're going to be getting actually these pairs. So I have not shown the whole procedure here because this is actually the same as before. So if we compare 8 with 6, we're going to get more than 1 bit difference, so we will discard that. But if we compare 8 with 9 or 8 with 10, then we're going to get something like this one. So for 8 and 9, 1 0 0 dash, and for 8 and 10, 1 0 dash 0. So this is the basic scenario after we're done with the comparison for group A and B. Alright, so here we can see that from group A and B we're actually getting these results. So the same thing will be followed for group B and C. Remember, we're only going to compare one group with its immediate next group. So for the next comparison, we're going to be comparing all the main terms of group B with all the main terms of group C. So we're going to compare group B and C, and the results will be seeing something like this. Alright, so 6, 7, we'll get this pair, and we'll also get 9, 11 pair, and we'll also get 10, 11 pair. All of these pairs actually match the condition of single bit differences. That's why we actually put them in step 3. So after that, we're going to be comparing group C with group D, and you can see that from the comparison of group C and D, we'll get the pairs of 7 and 15 and 11 and 15. So this is how we're going to be putting numbers in our step 3. So we're going to find single bit differences within our comparison, and then we're going to put that pair into our next step, step 3. So here from group A and B we got these pairs, and from group B and C we got these pairs, and from C and D we got these pairs. So this is what our problem looks like after we're done with the first phase of comparison. right? So this is step 1, step 2, and step 3. So now what we're going to do is that when we're done with the step of finding out single bit differences, in this case step 3, we're going to go back to the previous step, that means step 2, and put tick mark beside some of the numbers. Okay, so we're going to put some tick marks over there, step 2. So how will we actually put that? So let's see the rule. So we'll put tick marks beside those numbers on step 2 which we have taken as pairs in step 3. So what does it actually mean? That means you can see that in step 3 the first pair was 1 and 9. So we're going to go back to step 2 and we're going to put tick marks on 1 and 9. Alright. So next the pair is 4 and 6. So we're going to put tick marks on 4 and 6, just like that. Okay, so we're gonna do the same thing for all of those pairs. So let's continue. So for 8 and 9, we have put tick marks on 8, and the 9 was already ticked, so we did not put another tick mark beside that because it was already done. All right, so after that 8 and 10, yeah, so you can see that we have put tick marks on 10, and the same thing will be done for all other numbers. All right, so what we're doing right here is that whenever we're checking a pair, so like for example this pair is actually 7 15 right over there, and we're gonna go back to step 2 and we're gonna put tick marks on both 7 and 15. So the 7 was already ticked before, so that's why we have not touched it again, but the 15 was not, so we just put a tick beside 15 over there. Okay, so this is what we're saying right over here on this rule. So after after going through all the pairs and putting ticks, let me just show you the last one, 11 and 15. So both of these numbers are actually already checked, so that's why we don't put multiple ticks over there. All right, so after checking all the pairs like we did here, so we're going to move on to step 4 now. All right, so let's move on to step 4. So now we're going to find double bit differences. So what does it actually mean? It means we're going to check two different conditions. So we're going to check whether the dash position actually matches or not, and then another single bit difference. So let me just show you, it will be much easier. So basically what we're going to do is that we're gonna compare all the minterms of group A, all the pairs of minterms of group A with all the components of group B, just like before. We're gonna compare it group wise. All right, so then we're gonna compare group B with group C. Definitely it means that we're gonna compare all the elements of group B with all the elements of group C. Okay, so to compare that, we have to follow some conditions. We have to follow actually two conditions. So first we have to match the dash positions. All right, first we have to match the dash positions. That means when we are comparing the first pair over here, so 1 9, so we're going to compare these binary number with the binary numbers existing in group B. So to do that, at first we're going to compare the dash position. So if the dash position actually matches, all right, then if the dash position actually matches, then we have to look for single bit difference. That means except the dash. The dash is already indicating a single bit difference, right? So what we're gonna do is that while comparing, we're gonna try to find out whether the dash position actually matches or not, and then if it matches, then we're gonna look for another bit difference. All right, so that's how we're actually saying it as double bit difference. All right, so let's just see the example of how it works. So let's say the first two pairs right here. So the pair of 1 9 from group A is being compared to a pair of group B 6 7. Alright, so I have written the binaries over there. So you can see that the dash position doesn't match. For the first number, the dash position is the first position, and the second pair we can see the dash is at the 4th place. So the dash position definitely doesn't match, and since it doesn't match, so we have absolutely no need to check the second condition right now, and it can be discarded. All right, so let's check the second pair. So 1 9 is being compared with 9 11, and you can see the dash position doesn't match, so we're going to discard that one too. So let's move on to the third one. So 1 9 is compared to 10 11, and you can see that the dash position doesn't match here too, so we are also going to discard that. Alright, so we have compared the first pair of group A with all the pairs of group B, and we have not been able to match the first condition, the dash position match. Alright, so we have not been able to match the first conditions, that's why we didn't go through the second condition, and all of these comparisons were discarded. So let's see what happens next. So now I'm going to check the comparison for 4 and 6 pair. Alright, so for 4 and 6, you can see the numbers written here, the binary numbers. So first 4 and 6 pair, it is compared with 6 7. So you can see the binary numbers over there, and the dash position definitely doesn't match. So since it doesn't match, so we're going to discard it just like before, and we're going to move on to the next comparison. So now we're gonna move on to 4 6 and 9 11. Okay, so you can see right there that for both of those pairs the dash is exactly at the third place, so the dash position definitely matches without any doubt. So yeah, just like that, the dash position definitely matches. So the first condition actually matched. So since the first condition matched, now we're going to try to satisfy the second condition. That means if the dash position matches, then we have to look for single bit difference. Alright, so the dash position matched. Now we're going to see whether we have a single bit difference over here. So you can see that there is a bit difference at the first position, and there is another bit difference at the second position, and another bit difference at the last position. So you know, there is actually no single bit difference. There are actually 3 bit differences for those pairs. So even though the first condition matched, the second condition didn't. So we're definitely going to discard those pairs. We're definitely going to discard this comparison, and we're going to move on to the next one. Alright, so you get the idea, I guess, that for a valid comparison you need to match both of these conditions, not only one. Alright, so let's move on to the next one. So here you can see that 4 6 is compared to 10 11. The dash position didn't match, so we're definitely going to discard this one. Okay, so we are going to continue the same thing for this 8 9 pair now, and we can see if we continue our comparison, then the 8 9 pair will actually match with the 10 11 pair over here. So let's see how it can be done. So you can see the binaries. So you can see that the dash position actually matched right there. Both of the dashes are at the 4th place, so the dash position matched. Yeah, first condition matches. So now let's see whether the second condition is satisfied or not. So here you can see that we're getting only 1 bit difference, only the third position right there, only this bit is different for both the pairs. Alright, all other bits are actually same. So you can see that for this case our dash position actually matched. Okay, so let me just rewind it. So at first the first condition matched, the dash matches. Alright, so since it matched, now we're going to find a single bit difference. We're going to see whether there is a single bit difference for these pairs, and you can see that there is only 1 bit difference. That means it's a single bit difference, and since both of the condition actually match, that's why we're going to consider these pairs, and we're going to put them into our next step. So let's see how we can do that. Okay, so once we get such scenario, we're gonna put those pairs into step 4. So here we have put both of those pairs into step 4, and we'll write them together, 8 9 10 11, and we have written something over there. So let's see how we actually did it. So the previous dash will stay as it was. Alright, so that means the dash which was already there, this is the dash, the fourth at the 4th position, this dash was already there, so it will stay as it is. We will not touch that. Alright, so we're just going to put a new dash where we're getting the new difference. Alright, so we're getting the new difference at the third place, so that's why we put a new dash over there. Alright, and the rest of the numbers stay same. So that's how we're going to put our new sets of pairs into our step 4. Alright. Okay, so if we continue our checking, we'll be seeing that the 8-10 pair of group A also matches with the pair of 9-11 from group B. You can see that the dash position actually matches. Both of the dashes are at third position, and we can also see that there is only one bit difference over here. Alright, so dash position matches and there is only one bit difference, so we're gonna put them into our step 4 too. So here, just like that, 8-10 and 9-11 all join together, and previous dash will stay as it is, and for the new difference we'll put a dash over there. That's it. So that's how we're going to be putting numbers into step 4. Okay, so you can see a thing over here, both the rows look exactly same. That means both of these rows look exactly same. The binary numbers, actually the binary numbers and the dashes look exactly same. That's because if you see over here, you can see that all of those numbers are actually the same. 8, 9, 10, 11 or 8, 10, 9, 11, these are actually the same thing. That's why these numbers look exactly the same. Okay, so let's move on. So you can see that once we're done with the comparison from group A and B, I mean when we're done comparing all those main terms of group A with all those main terms of group B, then we're gonna be getting only these pairs into step 4. So from group A and B, we're gonna be getting these numbers into step 4. So let's see what we can get from group B and C. Okay, so you can see that I have not written anything here for group B and C. That's because none of the pairs satisfies actually both the conditions. So no match was found, so nothing was entered into step 4. Okay, so you get the point, right? That we're only going to put numbers into step 4 if we can somehow match both conditions, the conditions we have explained a few minutes before. All right, so since from group B and C there was no match found, none of the pairs actually matched both conditions, so we have not took anything from group B and C, and that's why there is nothing written over here. All right, so that's how we're gonna be done with group with all the group comparison from step 3. So that's it. Now we are done with step 4. Okay, so let's move on to our next step. So this is what our math looks like right now. So if you can remember, we have actually put some tick marks beside step 2 when we're done with step 3. So now that we're done with step 4, so what should we do? We should definitely put some tick marks beside some of the numbers of step 3. So how are we going to put those tick marks, and where will we put that? So let's check. The rule says we'll put tick mark beside those pairs in step 3 which we have actually taken into consideration in our step 4. So let's see the example how it works. So for the first number right there, 8, 9, 10, 11. Alright, so 8, 9, 10, 11. So we have written these numbers because we actually took into consideration two of the pairs, 8, 9 and 10, 11. So we're gonna go back to step 3 and we're gonna put some tick marks beside those pairs, 8, 9 and 10, 11. Alright, so let's check the next one. So the next one says 8, 10, 9, 11. So we're gonna go back to step 3 and we're gonna put tick marks on the pairs of 8, 10 and 9, 11. Alright, so we just put some tick mark beside those pairs which we have actually taken into step 4. Alright, so this is how the tick marks are placed. You should really check one thing that's written over here. So we have not put any tick marks beside the pairs 1 9 or 11 15, say. So let's check the 1 9. So you may think that I can see that there is a 9 over here and we have taken 9 in our step 4, so why didn't we put a tick mark beside that? Because in that pair we can see that we have only taken 9 from this pair into our step 4. We did not take 1. Alright, so to put a tick mark beside a pair, you need to take both of the numbers of that pair. So for example, for 1 9 or 11 15, we can see that one number is actually taken into step 4 but not the other, so that's why we did not put tick marks beside those pairs. Okay, so for the pairs of 8 9 8 10 9 11 and 10 11, all the numbers are present in step 4, as I have said. That's why we put tick marks beside those. So this is what our math looks like right now after completing step 4 and putting tick marks beside step 3. So let me ask you a question. So can we do a step 5 for this problem? We have already done 4 steps, step 1 2 3 4. So can we do a step 5? Okay, so the answer of this question is that we cannot. So why is that? Why can't we just create a step 5? That's because, as you see, that in step 4 there is only one group visible over here. Alright, only one group. So if there is only one group, then how can we compare that group with another? Because there is only one group. Remember, we actually compared group wise. Alright, so we compared A with B and B and C, and B with C and C with D and so on. So at step 4 there is only one group. So since there is only one group, we definitely cannot compare it with itself. So that's why we cannot compare further, and that's why there will be no step 5 for this problem. So now for our next task, we're going to consider those terms in our problem which don't have tick marks beside them. Alright, so this will check for step 2, 3 and 4. So we'll ignore step 1 because step 1 is basically just sequential ordering of all the main terms, so there was no groups involved, so that's why we're gonna ignore step 1. And so we're going to consider those terms which don't have tick marks beside them from step 2, 3 and step 4. These terms are actually important because these terms are known as prime implicants, and our next part of the problem actually depends on those prime implicants. So let's move on to our next task. So this is the math of how it looks like currently. So if we only consider the terms where there is no tick marks beside them, then we'll be getting something like this. So these are the terms which didn't have any kind of tick marks beside them. You can actually go back and check for yourself. So for 1 9 4 6 and 6 7 and 7 15 and so on, 11 15 and 8 9 10 11 and 8 10 9 11. So these were the terms which didn't have any kind of tick marks beside them. So that's why we have taken those terms into consideration and we have named them as prime implicants. Alright, so you may have one question that we have written only 8 9 10 11, so why didn't we take 8 10 9 11? Well, basically they are the same thing. Alright, they're the same thing, they have the same representation, so that's why we just ignored the redundant terms and we have taken only once. Alright, so these are the terms which didn't have any tick marks beside them, and these are called prime implicants. Okay, so these are the pairs and these are the binary representation for them. Okay, so we're also going to represent them using variables. Alright, so we're going to represent them using variables now. So in our question, if you can remember, the variables were written as w, x, y, z. You can actually rewind and go back to the question if you want. So the variables, the function was actually defined as w, x, y, z. So these are the variables and we're going to represent these binary numbers using those variables. So let's see how we can actually do that. So these are the main terms and these are the binary numbers and we're going to represent them using variables. So for our convenience, let's just consider the variables over here, w, x, y, z, and we're going to write them over there so that we can understand better. Okay, so For the first one, okay, for the pair of 19 dash 001, so how can we actually represent that? So what we're going to do is that we're going to ignore the dash, okay, we're going to ignore the dash and represent rest of the bits using corresponding variables. That means as we can see that there is a dash at the first place, so we're going to ignore these variable, we're going to ignore w completely, and for the rest of the stuffs we can see 001, and these we know how we can actually represent them. Okay, for 0 we can write it as x prime, for this 0 we can write it as y prime, and for this one we can write it as z. Alright, so that means our total representation will look something like this: x prime, y prime, z. So for the dash position we have actually completely ignored the corresponding variable, and for the rest of the bits we just considered the variables and written them as it is. Okay, so x prime, y prime, z. So let's consider the next one. So here's the next one for 4601-0. Okay, so the first 0 is written for w, so that's why w prime. The second at the second position we get 1, so this is written for x, that's why I have written x over there. Okay, and you can see at the third place there is a dash, so we have ignored y completely. All right, so and move on to the next one, we get 0, so that's why we have written z prime. So whenever we get a dash we're gonna ignore that, and we're gonna represent all rest of the bits using the corresponding variable. Okay, so by following this same procedure we can actually represent all of the pairs, and this is what it will look like after we're done with the representation with corresponding variables. Okay, alright, so we're done with the representation of prime implicants. So now we're gonna move into our part 2 of this problem. So the part 2 indicates selection of prime implicants, the setup, optimizing the tabular method. That means we have already gone through the first part of our problem. Now we're going to try to optimize it. Alright, so let's move on to our next part. So at first we're going to create a new table here. Okay, the table will look something like this. So the table will have some rows and columns. So what are we going to put in the rows and columns? So the mean terms which are given in the question, so here's the question I have written for your convenience. So the mean terms given in the question will be written as column values. That means we're gonna put them in the columns, and just so it gets better for our understanding, I have written them in sequential order. All right, so 1 4 6 7 8 9 10 11 and 15, these are the mean terms that were given in the question. And what will be written in the rows? Here you can see the prime implicants which we have just derived a few moments earlier. These prime implicants will be written as row values. Alright, that's why we actually calculated our prime implicants. So the so for our table the row values will be the prime implicants. You can write them in any order you like, and for columns you will write the mean terms given in the question. Okay, so just for convenience I have written them in sequential order. Alright, so let's move on to our next task. So now we're going to put a specific symbol for each individual prime implicants. So the symbol is actually marked as X. Okay, we're gonna call it basically it's a cross sign. So basically it's a sign indicating cancel or something like that, but we're gonna call it X. Alright, so we're going to put this symbol for all of those prime implicants, but not everywhere, for some specific positions. Okay, so for example, consider the first prime implicant over there, x prime, y prime, z. So x prime, y prime, z, this prime implicant was derived for the mean term pair of 1 9. So let me just move on to a few steps before. So you can see x prime, y prime, z was written for 1 9 for this pair. All right, so this is what is written over here for the mean term pair of 1 9, x prime, y prime, z. So we'll put x in place of 1 and 9. Alright, we'll put x in 1 and 9. Okay, so let's put this sign over there for 1 and 9. Okay, so we're gonna do the same thing for all of those other prime implicants. All of these prime implicants are actually derived for some of the pairs, right? So we're gonna put this sign for all of those prime implicants to their corresponding positions. So this is how our table will look like when you complete putting x in all necessary places. That means w prime x z prime, this prime implicant was derived for 4 and 6, so that's why we have put this symbol at the position of 4 and 6. Let's say the last one, wx prime, so this prime implicant was derived for 8 9 10 11 pair. Alright, so that's why we have put this symbol in the position of 8 9 10 and 11. Alright, so this is how we're going to complete the first step of this table. Okay, so this is what our table will look like when we're done with all the possible with all the placement of all possible symbols in this table. Okay, so this is what our table will look like after we complete putting all the x's in the necessary places. So let's move on to our next task. So our next task would be we're going to find out all of those columns which have only one x in them. Alright, that means we're going to, there are different columns 1 4 6 7 8 9 10 11 15. There are different columns definitely, so we're trying to find out those columns which have only one x in it. Okay, so we're going to find them and put a circle around that x. So let's see how we can do that. Say for example, you can see that these circled x's are the are actually those columns, are actually those places where we can see that there is only one x in that specific column. So let me just roll back. So this is the actual table and I want to find all those columns which have single x in them. Alright, so you can see at the first column, this one numbered column here, so you can see that there is only one x throughout this whole column. That's why I'll put a circle around this x. Same goes for this fourth column. So let me just show you. So I have marked all of those x's which are currently staying just as the single one in that specific column. Okay, so I have put circle around them. So now what we will do, now we're going to put a straight line through the columns and rows where we marked those circles in the previous step. Alright, so I've already marked some x's and now we're going to put a straight line through those marked places, both row wise and column wise, and we're also going to put a tick mark at the end of the column just to keep track. So let's see what I'm saying. So I can see all those marked places, so I'm going to put some straight lines over them. So in our case those columns are basically 1 4 8 and 10. So let's see how the straight line looks like. Okay, so you can see that for the first column over here, for the first circled element over here, I have put a straight line through the column and also a straight line through the row. So we'll put straight lines through the columns and rows for those marked places, and when we're doing that, we'll also put a tick mark at the end of the column so that we can just keep track that this column is done. Alright, so we're gonna do the same thing for this x at column 4 and this x at column 8 and this x at column 10. Let's see. So you can see the fourth one is done, and now the eighth one is done, and now the 10th one is done. Okay, so the row was already cancelled out. The row was already cancelled out when we did the 8. That's why for the 10th one we just cancelled out the column. Okay, so this is how we're gonna do our first phase at this table. Alright, so let's see what we can do next. Okay, so another thing, you may ask that why we are actually putting straight lines over all those columns, why we are actually putting tick marks right underneath them. Okay, so our final target is to put straight lines through all the columns. All right, let's see how we can actually do that, and to keep a track of what we are doing, that's why we are actually putting that tick marks, so that we can understand when we're done with all the columns. Okay, so let's move on to the next task. So right now we have only circled and cancelled out some of the x's, right? Some of the x's from this table. So for doing so, we have actually cancelled out some other x's indirectly. So let's see what I'm saying. So for example, when we actually cancelled this x over there at the fourth column right over there. All right, so when we actually marked this x and then we cancelled this whole column and this whole row, then we just cancelled out this x over here at column 6 indirectly. You can check this out. Let me just go back one step. So I actually just cancelled out this fourth column and this corresponding row. I did not touch this x over here at column 6, but since I just cancelled out this whole row, that's why this x over here got cancelled out indirectly. So that's what I'm talking about. Okay, so this x over here got cancelled out indirectly, and the same way this 9 over here, so sorry, this x over here at column 9 and this x over here at column 9 too, so both of them actually got cancelled out indirectly. All right, we have not directly touched them, but they were cancelled out indirectly. And the same thing can be said for this one too. This one over here at column 11, so this was also cancelled out indirectly. So these are the x's. Okay, so these are the x's which were actually cancelled out indirectly. So now we're going to go to those x's and we're going to cancel their columns, only their columns. Okay, so we're going to put straight lines through those columns only. So for example, we're going to go to this place. This x was cancelled out indirectly, so we're going to put a straight line over there throughout the column. Remember to put straight line only through the column because the row was already done. All right, there's nothing to cancel anymore, so you can just put a straight line throughout the column. So the same thing will be done for this 9th column, and the same thing will be done for this 11th column, because there were some x's which were actually cancelled out indirectly. All right, so we just go to those places and we just put a straight line throughout those columns, and that's it. Since we put some straight lines over those columns, so we'll also put some tick marks underneath them so that we can keep track. And here it is. Okay, so as you can see that we have already put tick marks over most of the columns. Remember, our target is to cancel actually all the columns. So basically we need to reach a destination where we can see tick marks underneath all the columns. So we're actually going nearer to that destination. Okay, so there's still column 7 and 15 left, right? So till now what we have done, let me just give you a short review. So at first we found out the those columns which had only single x in them, and then we marked those x's. Here you can see the circled x's, and then we put straight lines throughout that column and then that row for all those positions. Okay, so we did that. Here it is marked in red, and after that, when we're done with that, then for that step we also see that there were some other x's which were indirectly cancelled out, like this one over there for 6, and this one over there at 9, or this one, or maybe this one here at 11. So these are the x's which were actually indirectly cancelled out for our previous step. So we go into those places and we just put a straight line over those columns. Okay, only the columns. So the green straight lines are actually indicating those. So till now we have done that. So even after following these two steps, column 7 and 15 still got untouched. We could not touch column 7 and 15. We could not do anything to the axis of column 7 and 15. So we need to cancel those columns too. So how can we actually do that? Okay, so in such cases, firstly we need to take a look at the x signs which remained untouched. That means in this case there are two x's in column 7 and there are two x's in column 15. These remained untouched, so we need to take a look at them. All right, so now what we're trying to find is we're trying to find such an x. Okay, we're trying to find such an x that if it is circled, then we'll be able to cancel out all other remaining x signs. All right, so that means among those untouched x's, we need to find such an x for which if it is cancelled, if we can somehow circle it, then we'll be able to cancel out all other remaining x's. So there's a point to remember over here, that remember circled x means we can put a straight line on both row and column. Alright, so whenever we circle an x, we can definitely put a straight line through the column and the row. Alright, so both row wise and column wise. So that's what we're trying to find. We're trying to find such an x that if it is circled, then we can somehow cancel that x, including all the other remaining x's. Okay, so let's see how we can do that. So in our case, we can see that these x over here at column 7 and these x over here at column 15, both of these x's actually match the condition what we're trying to do. All right, so in this case such x can be this one or this one too. So for our example, let's just consider this one, the yellow sign one. So let's just consider this one. Let's see what happens. Okay, so I'm gonna put a circle around that since I consider this x. Okay, so since I put a circle around this x, now I can cancel this column and this row, right? So let's just cancel it. Yeah, I'm gonna consider this one, and now I'm gonna cancel the column and the row. All right, so now we can see that column 15 is actually cancelled out too. All right, so we'll put a tick mark underneath it. So now if you look carefully, you will see that since we cancelled out this column and this row, this black line here over here, so it actually helped us to eliminate this x indirectly. All right, so this is what is written here. So look carefully, this x got cancelled out indirectly. So what do we actually do when an x gets cancelled out indirectly? You remember? Well, we actually put a straight line through that x throughout the column. Okay, only the column, remember. So let's do that. Since this x got cancelled out indirectly, so we're gonna put a straight line throughout this column only. Okay, so yeah, so we have put a straight line over this column, and since this column was cancelled out too, that's why you put a tick mark over there at the end of the 7th column. So all of our columns now got cancelled out, and we have reached our target, right? Because we want to reach this destination where all of our columns are cancelled out. So the same thing could also be done if we selected this x instead of this one. It will also have the same actual effect. All right, you can actually check this out for yourself. So we're keeping this for you. All right, but we have shown one possible way. All right, so let me just answer some important questions what actually students ask in most of the cases. So what would happen if we didn't choose any of those x's? All right, so what would happen if we choose say this one? All right, what would happen if we chose this x over this or this one? Okay, so let me just show you the simulation. It will be much clearer in the simulation. So if we consider this x where my mouse cursor is, so then At first I would cancel the column, and I would also cancel the row, but as you see, if I cancel this column and this row, then this definitely doesn't help this x's at column 7. Alright, so these still remained untouched, so that's why we actually can't select this one. That's why we had to find such an x for which all the other x's can be cancelled out. Alright, that's why we can't actually select this x over here. Okay, so that's why we didn't choose this one, and the same can be said for this one too. If we chose this x, then we would also have some type of similar issues. Okay, so there are some other questions too. What would happen if we don't get such an x that would help cancel out all the other x's? Alright, so in that case, the best we can do is to find an x which will help us to cancel out most of the remaining untouched x. That means our first target is to choose such an x which will help us eliminate all other x's. But if we can't find that by any way possible, then we're trying to find the x by which we can actually eliminate most of our x's. All right, and what would happen if we cannot cancel out a column even after following all those possible rules? That means, what if we have followed all the possible ways, we have followed all the possible rules, but still we can't find any possible way to cancel out a column? Well, this is very unlikely, but if you ever get such a case, then you are going to circle the x found in that specific column and then cancel out that column. However, we can only do this if there is absolutely no other way to cancel out that column, meaning we have tried all other possible ways. So hope you understand. So these are some of the important questions that students ask during this lecture. Okay, now let's get back to our actual correct solution over here. Okay, so this is the solution we have actually calculated throughout this lecture. So now since our solution is almost done, so now is the time for our answer. So what would we get from this long problem over here? So since all the columns have been cancelled out, so we just need to find the answer now. So to get the answer, we need to follow a specific procedure. So we need to look at those circles over here and take out the corresponding prime implicants. That means as you see, there are different circles over here, right? There are some x's which are marked with circles. So we're going to look at those circles, and we're going to take the corresponding prime implicants from them. So let's see. For the first one over here, the prime implicant is x prime y prime z. So we're going to take this out, x prime y prime z. All right. So for the second one over here, we can see that it's w prime x z prime, and for the third one over here, we can see the prime implicant is x y z, and the fourth one, you can see that both of these x's are actually indicating to the same prime implicant, so w x prime. So what we'll do, we'll take those corresponding prime implicants out, and then we're going to put or sign among them. Okay, we're going to put plus sign among them. So basically our answer will look like, our final answer will look like something like this one. So at first x prime y prime z, then for the second circle we get w prime x z prime and put plus sign among them, between them, and then we get xyz for the third circle here, and for the final marked x's over here, we get wx prime. So here we'll write those prime implicants and we'll put plus sign among them. So this is the final answer we are getting: x prime y prime z plus w prime x z prime plus xyz plus wx prime. So this is the end of our tabulation problem, and this is the final answer we are getting. Thank you everyone.